All right, so this is derivatives and integrals of these power series, which sounds like intimidating, but you all know how to take a derivative and an integral. So it's like it's not new information. It's the same thing as before. For the derivative, you just take the derivative of each term, which is just the derivative of what's there. Integral, you're going to take the antiderivative of each term. Here's like the big takeaway or the big concept here, because again, you know how to take derivatives and antiderivatives. The function, the derivative, and the integral will have the same radius of convergence. So what we're going to do is like the last problem on your quiz. You only have to do the ratio test once, because once you get the radius of convergence, it's the same for all of them. They just might have a different interval of convergence, and you have to check the endpoints for each of them. So like, for example, f of x might include the endpoints and the derivative might not. Does this make sense? Like, so you only have to find the endpoints once. You just have to check them for each one of these, okay? So we're going to find the radius and interval of convergence for the function, the derivative, and the integral. So the function is this power series, like, an infinite number of terms. We're going to do the exact same thing we just did on the last questionnaire quiz. Just going to practice it again, all right? So limit as n goes to infinity, gigantic absolute value. We're going to plug in n plus 1. So x to the n plus 1 over n plus 1. And then that's all over the series itself. On the quiz, it should have been 6. Does that sound familiar? Okay. Yeah. R was 6. All right, so we're going to flip this over. So it'll be x to the n plus 1 times n over x to the nth times n plus 1. So just doing the reciprocal. You just do this so many times, you're going to get so used to it. All right, and then we're going to look for what cancels out. All the x's will cancel except for one of them. So we end up with x in the numerator, and then the n and the n plus 1 don't change. There's really nothing you can do to that. And then you're going to evaluate the limit. As n goes to infinity, well, this is n to the first and this is n to the first. When it's the same, you use the coefficients, which is just x. And so you just get absolute value of x. I barely fit it in there. And that has to be smaller than 1. So we are centered at 0 and our radius of convergence is 1. So r is 1 and it'll look like this. Our endpoints are -1 and positive. Good news is we're not going to have to do that again. The endpoints are -1 and +1, period, end of story. That's not going to change. All right. So let's check x equals -1 for this original function. You're just going to go back and plug in -1 for x. And we're going to decide whether that converges or diverges. So what do you think? It does converge. Why? Yeah, alternating series test. We're at the point where I'm not going to make you write it all out. Converges by alternating series test. Obviously, on the AP exam, I recommend you write out every last little thing. I think we know it at this point, okay? Now, if it was a +1, it would diverge, and why is that? It's a harmonic series, or you could say P series where P equals 1. And actually, that's what's going to happen here. If you plug in 1 for x, you'll have 1 to the n, which just is 1. And so this diverges because harmonic series. So your interval of convergence is that we want to include the -1, but not the +1. So that's exactly what we've done before. Now we're going to do the derivative. So I would just separate that with a line. And we're going to do f prime of x. The only tricky thing about this is you have x and you have n. You're doing the derivative with respect to x. The n is sort of just there. So whenever you do this derivative, here, let me just ask you before I tell you the answer. You're doing the derivative of this right here. It's really just a power rule. What would that be? n, and then you would subtract 1. Good. So it'll be n x to the n minus 1 over n. Like the n is sort of just there. And then those n's are going to cancel. Oh, I am so sorry. I forgot to write the sigma. I apologize. I got so excited to take the derivative, I forgot to write the sigma part of it. So it's really just a power rule. You bring the n down and then you drop a degree. And then those n's are going to cancel. That's really all that there is to taking a derivative of a power series. Like doing a derivative of a power series sounds like this really complicated thing. That's all it is. You know how to take a derivative. It's just, it looks complicated with the n's in there. Now you don't have to do all of this again. R is 1. All we have to do is test these two endpoints again. So let's test -1. So you're going to plug in -1 for x. So that'll give us -1 to the n minus 1. And we just have to decide, does that converge or does that diverge? So it diverges. You're going to end up with -1 plus 1 minus 1 plus 1 minus 1 plus 1. That's not really like any particular test. That's just not going to work. And then I'm going to write the +1 over here instead of underneath so that I make sure I end up with enough room here. If you plug in +1, 1 to the n minus 1, I mean, that's just going to be 1. So you end up with 1 plus 1 plus 1 plus 1 plus 1 plus 1. It's going to keep getting bigger and bigger. So that's going to diverge as well. I guess you could say by the nth term test, like the limit is n goes to infinity, we go to, well, I don't know. It's just, it's not going to converge. And so the interval of convergence for the derivative would be that you want to leave both of them out. So see how it can be different? That's like the whole takeaway here, is that the radius of convergence would be the same, but the endpoints, whether you include them or not, could be different. And lastly, we're going to do the integral. What are you doing? You're okay. And again, this sounds like a really complicated thing, like, oh, we're doing antiderivatives with power series, but you're just doing the antiderivative of this. So you would add 1 to the power, it would be x to the n plus 1, and then what? Divide by that. And then this n is sort of just there. So it'll be x to the n plus 1 over n plus 1 times n. Oh gosh, thank you. Because as a teacher, the part that I'm teaching you is that, like, the sigma is just sort of like, oh, I forgot about that. I like want to extra focus on the part that's like new to you. Dude, are you finished with that?
Yeah, no, I'm done now. I feel bad.
What are you trying to do? Okay.
But I have it.
You have it right now? Okay. That's like when I get in the car after daylight savings time. Like I have to fix it right away before I can even like drive anywhere. It has to be correct. Okay, I'm gonna try to set everything I wanted to say there. All right, so again, R is still 1. We're just gonna test these endpoints. So we're gonna test -1. So plug in -1 for x. And then you have to decide, does that converge or does that diverge? So what are our feelings about that? Alternating series test, good. And again, on the AP exam, I would want you to write it all out. Limit as n goes to infinity of that equals 0. The n plus 1's term is going to be smaller than the nth term, et cetera, et cetera. But that's not like what we're covering today. What we're covering is the derivative and the integral part of it. All right, so then if you plug in +1, 1 to the n plus 1 is just going to be 1. Now this one's going to be a little bit more complicated because that's not an alternating series. What would you try? So that'll give you an n squared down there, which is where I want you to be thinking. We're going to compare it to a p series. So we're going to compare this 2, 1 over n squared. And the idea is you want to say, because that converges, this one converges too. That's where we're headed with, well, actually, does that converge? Sort of just told you. Good, okay. Converges, p equals 2, which is bigger than 1. And so we want to say, since that converges, this one converges too. I always do a limit comparison because direct comparison, you have to worry about which one's smaller and bigger and which one converges. Like, do you remember, like, if the bigger one converges, so does the smaller one? I don't know. I find that more complicated. I just always do a limit comparison. You just put one series over the other, and it doesn't matter which one is which, but put one of them over the other. And so then we're going to do the reciprocal of that. Here, I'll go ahead and distribute the n, like Jacob said. And so what is that limit going to go to? Good, because both the coefficients are 1, it'll go to 1. The rule is, since that's finite and positive, since this converged, that does too. I was just looking at an AP problem the other day because, you know, like, we're going to start AP review soon and like be working some of those problems. Well, they released, along with the scoring guides, like this fine print that went along with them. Like, oh, if you did this, you'll get this point. It's nice because it's really, really thorough. And so I was reading through the fine print on one of them. This showed up on there, a limit comparison thing. If you don't say that that value is positive, they won't give you the point. So anyway, I learned that, and I just told you, you know, sometimes I feel like we're just scrambling around in the dark. Like, I don't know to tell you that unless they tell me, kind of thing. Anyway, now I know, so I'm passing that on to you. This is positive, which I feel like, duh, right? Like, I don't know, but anyway, this is positive, so converges by limit comparison. And the reason that really makes me upset is how many other things are there like that I'm just, I don't know. Do you know what I mean? Like, frustrating. Anyway, so this interval of convergence, what did we say? They both converged. So we want to include both the -1 and the +1. So again, the huge takeaway here, like the main thing I'm trying to get across is they have the same radius of convergence, but the endpoints could be different. We're just going to try one more. Do you see why I only gave you 2 problems? Because, like, you really only need 2 of this to understand it. But let's try one more. What's that? It's all writing. It's like an essay. Well, I only gave you 2 because I feel like, yeah, I feel you on that. Stats is not my thing. Did you do the golfing today? How did you do? Okay, so we're gonna plug in n+1 and then put it over the series itself. And then we're gonna do the reciprocal. And you almost kind of need to separate those. Like, this is x to the n+1 over 3 to the n+1. So in the numerator, we're gonna have x to the n+1, and then this 3 to the n is what's gonna come up to the top with us. All right, so what can we cancel out there? Or what is this gonna reduce to, I guess would be a better way to say it. Over 3, perfect. And it's smaller than 1. So you would multiply the 3 over, and so r is 3. For all of them, we don't have to do that again. That's the same for the function, the derivative, and the antiderivative. Bless you. So we're centered at 0, r is 3, so we're gonna have to check our endpoints, -3 and +3. So if we plug x is -3 back into the original series, that will give us -3 over 3, which would just be -1 to the n. So same as on the other side of the paper, -1 plus 1 minus 1 plus 1 minus 1 plus 1, that's going to diverge. Sorry, that was x being -3. And then if x is +3, that'll just be 1 to the n, which is just 1. So again, 1 plus 1 plus 1 plus 1 plus 1 plus 1, that's going to diverge. And so the interval of convergence is that we don't want to include either of them. All right, so now we're going to take the derivative. Hey guys, look, I wrote the sigma. So you're going to bring the n down, and it'll be all of that to the n minus 1. But then what rule do we have to do? You have to chain on the derivative of the inside, which would be 1/3, okay? So it's going to be n x plus 3 to the n minus 1, and then that's all over 3. It's 1/3. You have to multiply on a 1/3 for the chain rule. But good news, you don't have to do the ratio test again. R is 3. We're just going to check our endpoints. So if x is -3, plugging -3 in for x right there, that'll just be n -1 to the n minus 1 over 3. Now it is an alternating series, but think about like what you would do for an alternating series test. The first thing you would do is limit as n goes to infinity of that. What's that going to give you? Infinity. So it's actually not an alternating series test. It's actually what test? Nth term test. It diverges by the nth term test. So even though it is an alternating series, it's not going to work out for an alternating series test. An nth term test shows it diverges. So then if you let x equal +3, if you plug in +3 for x, you have 1 to the n minus 1, which is just going to be 1. So you just end up with n over 3. And the exact same thing is going to happen. If you did that limit as n goes to infinity, you're going to get infinity. So once again, we can't include either of the endpoints. Hanging in there? I know it's Friday. We're almost done, right? Antiderivative. We're just going to finish this up and then I'm going to talk to you guys for a minute. Oh gosh, you did. Okay, yes, we're going to raise that by 1 and then it'll go over n plus 1. Now, it's not a chain rule, it's a U substitution. I wouldn't write out all of the U substitution steps, but to cancel out the 1/3, you would multiply by 3. you know, an integral and a derivative are inverses of each other. So you're gonna have to multiply on a 3. So that's your antiderivative. You raise the power by 1 and then divide by that. But again, you're gonna have to multiply on a 3 to cancel out the 1/3. It's an anti-chain rule. That's what use substitution takes care of that. But I would just think of it, oh, there's a 1/3 I need to multiply by it. And again, we're just going to check the endpoints. So if x is -3, that'll give us 3 times -1 to the n plus 1 over n plus 1. And so what's that going to do? Converge by alternating series test. I think that was the first one on this side of the paper that we got to converge. All the rest of them were diverges. All right, and then if you plug in +3, you're going to have 3 over 3, which is 1 to any power is just going to be 1. So it'll just be 3 over n plus 1. We're going to have to do a comparison test. See, you guys are getting to the point where you're thinking through it faster than you can even write it. Make sure you slow down enough to write it, because on the AP exam, you're going to have to. So we're going to compare it to 3 over n, which diverges because harmonic series. And the idea is you want to say, because that one diverged, the one we're looking at is going to diverge as well. That's the idea. It's like, oh, well, whatever that one did, the one we're comparing it to, this one's going to do as well. So I would do a limit comparison. You're just going to put one of the series over the other. The 3's are going to cancel, or you could leave them in there, really, it doesn't matter. But if you take that limit out to infinity, what's that going to equal? 1. And I learned the other day, you have to say that that's positive. I get so mad when I read stuff. I'm like, gosh, what do you want from us? 1. Positive, so diverges by limit comparison. Yeah, again, it's not I know that's so hard. You're like, oh, look, it came out to this thing that worked, so I want to say it converges, but it worked, so it does whatever the other one did. So since this one diverged, that one diverges as well. So our interval of convergence for the antiderivative was that we get to actually include one of these. Wait, we're including the -3, but not the +3. So again, the big takeaway is you have to check the endpoints because they could be different. But you still know how to take a derivative and an integral. There's just going to be n's all over the place, okay?